and welcome to the workshop. Today, we're diving headfirst into a world of intense heat, incredible pressure, razor-sharp precision. Imagine a place where raw, unyielding steel becomes a kitchen tool. Raw slab of steel. Finished cleaver on a kitchen counter. The air is thick with the rhythmic clang of hammers. Hot metal hitting quench oil with steam and hiss. Science-craft-wide factory floor showing both. Birthplace of the cleaver. Pull back the curtain on the process. Simple slab of metal. Perfectly balanced instrument. Sparks fly across the dim floor. A massive mechanical hammer slamming a glowing hot billet. The metal, heated to a malleable, almost liquid state, protests with a deafening roar. It yields, it spreads, it starts to take shape. This is not a gentle process. It is controlled, violent, and beautiful transformation. Every single strike is calculated, shaping the future blade with a purpose refined over centuries. Brute force and fine control, and it's just the first step. The smell of hot steel and quenching oil hangs heavy in the air. You can feel the heat radiating from the furnaces. Workers have learned to master that oppressive warmth. They move with a practiced, almost casual grace around machines that could crush a person in an instant. This environment is a testament to human ingenuity and our ability to command one of the Earth's strongest materials. We are going to walk through this symphony of fire and force, exploring each station and understanding the role it plays in making the tool you might find in your own kitchen drawer. This isn't just about bending metal, it's about instilling a soul into an inanimate object. The goal is to create a cleaver that is strong, durable, and holds a wicked edge. It needs to be tough enough to split bone, but precise enough for skilled hands to use all day. Every step we are about to witness, from this initial forging to the final polish, is a crucial piece of that puzzle. So, put on your safety glasses, and let's get closer to the action. So, what's our mission today? It's simple. We are going to demystify the entire process of making a cleaver, from start to finish. We'll follow a single piece of steel as it's cut, heated, hammered, cooled, ground, sharpened. I want to show you every critical stage in 15 minutes. We'll look at raw materials. Why this steel? What makes it right for heavy-duty, high-impact use? Without chipping, without becoming dull. It starts with the right ingredients. Next, heat treatment, the real science. Harden and temper correctly, or suffer brittleness or softness. Cleavers plunged into quenching baths, dramatic. Then tempering ovens, regain toughness, delicate balancing act. Then give it its edge. Grinding and sharpening stations, sparks fly. Abrasive belts, wheels. Define edge geometry, razor-sharp finish. Handles made and attached. Classic wood, durable composite, modern synthetic. Balance, comfort, safety. A great cleaver feels like an extension of your arm. Finally, rigorous quality control checks, durability and performance tests, safety protocols for workers. By the end, you'll understand and appreciate the work, skill, and science. You'll know what makes a quality blade. Let's get started. Everything we do here in the factory, all the fire and force, starts with one thing: the steel. You might think steel is just steel, but that couldn't be further from the truth. It's like baking a cake. The type of flour you use makes all the difference. For a cleaver, we need a specific recipe, a steel that can take a beating and come back for more. We're not making a delicate scalpel here. This tool needs to be tough, really tough. It has to smash through bone without chipping, but it also needs to hold an edge long enough to get through a whole day's work in a busy butcher shop. Finding that perfect balance is the first critical decision in making a great cleaver. The main ingredient in our steel recipe is iron, but the secret sauce is carbon. The amount of carbon in the steel determines its potential for hardness. Too little carbon, and the blade will be soft, bending easily and losing its edge in a heartbeat. Too much carbon, and the blade becomes incredibly hard, but also brittle, like glass. It might hold a razor edge, but the first time it hits a solid bone, it could shatter into pieces. So, for our cleavers, we typically use a high-carbon steel. This gives us that sweet spot, hard enough to stay sharp, with enough flexibility to absorb the shock of heavy chopping. But carbon isn't the only player in this game. Modern steels are alloys, a mix of different elements, each added for a specific reason. We might add chromium to the mix, which is a key ingredient in stainless steel. Chromium helps the blade resist rust and corrosion, which is a huge deal in a kitchen environment where things are constantly wet. Then there's vanadium, which helps create a very fine grain structure in the steel. A finer grain means you can get a sharper, more durable edge. Other elements like molybdenum can increase toughness, making the blade even more resistant to chipping under heavy impact. It's a complex chemical cocktail, designed specifically for this job. So, when the raw material arrives at our factory, it's not just any old chunk of metal. It comes in large bars or sheets, and each batch has a precise chemical composition that has been tested and certified. We know exactly what's in it, down to a fraction of a percent. This consistency is key to making a reliable product. Every cleaver that comes off our line has to perform just like the one before it. The journey from this simple, dark gray bar of metal to a gleaming, sharp-edged tool is a long one, but it all begins with making this crucial choice. The right steel is the foundation for everything that follows. Once we have our perfect steel, we have to decide how to turn that raw bar into the basic shape of a cleaver. There are two main roads we can take here: forging, stamping. Each method has its own pros and cons, and the choice often comes down to a balance between performance, tradition, cost. Let's break them down. Forging is the classic old-school method. It's what you probably picture when you think of a blacksmith, heating the steel until it's glowing hot and then hammering it into shape. Here in the factory, we use giant mechanical hammers that deliver thousands of pounds of force. Forging changes the metal at a structural level. As the hammer pounds the hot metal, it compresses and aligns the internal grain structure of the steel. Think of it like kneading dough. That makes the steel denser and stronger, especially at the points of greatest stress, like the edge and the bolster, where the blade meets the handle. The result: exceptional toughness and superior edge retention. A forged cleaver is the heavyweight champion, built for maximum durability. But it's also more labor-intensive, requires more skill, and costs more. It's a premium process for a premium tool. The other path is stamping. This is a modern, high-volume method. We start with a large sheet of steel and use a massive hydraulic press to stamp out the shape, like a cookie cutter on dough. It's fast and produces many identical blanks. There's no heating or hammering, so the grain stays random and uncompressed. Stamping is less expensive, lighter, and more uniform. So, which one is better? It depends. A stamped cleaver can be excellent. With modern steels and precise heat treatment, stamped blades can perform very well at a more accessible price. They tend to be lighter and a bit more flexible. A forged cleaver is top tier for professionals and brutal daily use. Here in this factory, we make both. That lets us serve everyone from the serious home cook to the professional butcher. Before a single piece of steel is cut or hammered, the cleaver exists as a blueprint. The design of the blade is a masterclass in functional engineering. Every curve, angle, ounce of weight has a specific purpose. The most obvious feature of a cleaver is its shape. A big rectangular block of steel. This isn't just for looks. The broad side of the blade, the heavy mass of the blade. It carries a huge amount of momentum, allowing it to chop through bone and cartilage with a single swing. The large, flat side can be used to smash garlic, or smash ginger, or scoop up chopped ingredients from the cutting board. It's a multi-purpose design born from pure utility. Next, the blade's profile. Then, the edge geometry. Unlike a chef's knife designed for slicing, a cleaver is a chopper, so the edge needs to be more robust. If it were ground to a very thin, acute angle like a razor, it would chip or roll on impact. Therefore, cleavers are ground with a wider, more obtuse angle. That produces a tougher, more durable edge that withstands high-impact collisions. The trade-off is it won't feel as slicing sharp as a thin knife, but that's not its job. Its job is to split things with brute force. The thickness of the spine, the top, non-sharpened edge, is a critical design choice. A thick, heavy spine adds weight and rigidity. That weight helps generate chopping force and prevents bending. Weight distribution is planned in the design phase. We place the balance point just in front of the handle to make the cleaver blade heavy. That forward balance lets gravity and momentum drive the blade with less effort from your arm. Finally, the handle design. The tang extends back from the blade and goes inside the handle. A full tang runs the full length and shape of the handle sandwiched between two handle scales. This construction gives strength, better balance, and prevents separation under extreme use. Every detail is thought out before production begins. When you pick up a great cleaver, it should feel like it means business. That feeling comes from a deliberate combination of weight balance, ergonomics, all decided right here in the design stage. The overall weight is one of the most important factors. A heavier cleaver carries more momentum into the cut, making it easier to chop through bone and tough joints. Too much weight can make the tool unwieldy and fatiguing to use, especially for a professional who might be swinging it for hours. So, we have to find that perfect middle ground, a weight that provides power without being a burden. This is often a matter of ounces. The balance of the cleaver is just as important as its total weight. We generally aim for a forward balance. Center of gravity, an inch or two in front of where your hand grips the handle. This forward bias makes the blade want to fall forward, amplifying the power of your swing. It feels like the cleaver is helping you chop. Achieving this balance is a careful dance between thickness of the blade, tapering of the steel from the spine to the edge, and the weight and material of the handle. We tweak the design by adjusting the thickness of the tang or changing the shape of the bolster to shift the balance point. Then there's the handle itself, the part you actually connect with. The handle design is all about ergonomics and safety. It needs to fill your hand comfortably, providing a secure grip even when your hands are wet or greasy. The shape must prevent slipping forward onto the sharp blade. We use materials like rosewood G10 micarta. Composites are incredibly durable and waterproof. They also provide excellent grip, a popular choice for heavy-use professional tools. The handle is often contoured to fit the natural curve of a gripping hand. Ultimately, the goal is a tool that feels like a natural extension of the user's arm, a fusion of power and control. The design must inspire confidence. You should feel it's a solid, reliable instrument, capable of doing its job safely and effectively. All these decisions, weight of the steel, balance point, curve of the handle, texture of the material, are made long before the forge is ever lit. They form the soul of the cleaver, a blueprint for a tool designed not just to cut, but to perform. This thoughtful design separates a truly great cleaver from a simple slab of sharpened metal. Now we arrive at the heart of the factory where the real transformation begins. This is where raw steel meets incredible heat and immense pressure. For our forged cleavers, the process starts at the furnace. The pre-cut bars of high-carbon steel, called billets, are loaded into a massive forge that burns at over 2,000 degrees Fahrenheit. The steel soaks in this intense heat until it glows a brilliant, almost blinding yellow-orange. At this temperature, the rigid crystalline structure of the steel relaxes, making it soft and malleable, almost like modeling clay. It's ready to be shaped, and there's no time to waste. The steel must be moved quickly from the fire to the hammer before it loses its workable heat. With a shower of sparks and a deafening boom, the first blow lands. A worker, using long tongs, positions the glowing billet under a gigantic power hammer. This mechanical behemoth can strike with a force of several tons, far more than any human blacksmith could ever muster. Each impact violently compresses the steel, forcing the metal to flow and spread. The worker skillfully rotates and repositions the billet between strikes, expertly guiding the transformation. The rectangular bar begins to flatten and widen, slowly taking on the recognizable, blocky silhouette of a cleaver blade. This is not a random beating. It is a precise and practiced choreography of force, heat, and skill. As the hammer continues its rhythmic assault, it does more than just change the shape of the steel. This violent compression fundamentally alters the metal's internal grain structure. It refines the lines and packs the grains tightly together. This process, known as grain flow, creates a continuous, uninterrupted structure that follows the contours of the blade. This is what gives a forged blade its legendary toughness and resilience. The steel becomes denser and stronger, particularly along the future cutting edge. You are literally watching the strength being hammered into the very soul of the blade, creating a tool that can withstand decades of hard work. For a stamped cleaver, the initial shaping process is much less dramatic, but incredibly efficient. Instead of heating and hammering, we use a different kind of giant, a hydraulic stamping press. A large, cold sheet of steel is fed into the press, which is fitted with a hardened die in the exact shape of the cleaver. With immense pressure, the press punches out a perfectly formed blade blank in a single, swift motion. The process is clean, fast, and produces hundreds of identical blanks an hour. While it doesn't refine the grain structure like forging, it creates a precise starting point for the next, most critical step in our journey: heat treatment. Both paths lead us here. Section 2. The critical quench. Whether forged or stamped, our cleaver blank is still in a soft or annealed state. It has the right shape, but it has no backbone. You could easily bend it or scratch it with a file. To give it the strength it needs, we have to perform some metallurgical magic through heat treatment. The first step is called hardening, or austenitizing. The shaped blades are carefully loaded onto racks and placed back into another precisely controlled furnace. They are slowly heated to a specific critical temperature, usually around 1,500 degrees Fahrenheit. This temperature is vital. It causes the carbon within the steel to dissolve evenly into the iron, forming a new internal structure called austenite. Holding it at this temperature ensures the entire blade is uniformly transformed. Once the blades have soaked at this temperature and the transformation to austenite is complete, the most dramatic moment in the factory arrives: the quench. This is the point of no return. The glowing hot blades are rapidly removed from the furnace and immediately plunged into a large vat of oil. The sudden, extreme cooling is a massive shock to the steel system. It doesn't have time for its internal structure to relax back into a soft state. Instead, the dissolved carbon is trapped, forcing the austenite to transform into a new, incredibly hard and brittle structure called martensite. The angry hiss and billowing smoke are the sounds of the blade's character being locked into place. The choice of quenching medium, in this case oil, is extremely important. Water cools very fast, which can create immense internal stress and cause the blade to warp or even crack, especially with a thick blade like a cleaver. Air cools too slowly and the blade wouldn't get hard enough. Oil provides a perfect middle ground. The temperature of the oil itself is also carefully controlled to ensure every single blade is quenched under identical conditions, guaranteeing consistency across the entire batch. After the quench, the blade is completely transformed. It is now glass hard. If you were to drop it on the concrete floor, it would likely shatter into several pieces. At this stage, it can hold an incredibly sharp edge, but it has zero toughness. It's too brittle to be a useful tool. A single hard chop against a bone would cause the edge to chip away like a piece of flint. We have successfully achieved maximum hardness, but in doing so, we have sacrificed all durability. The next step is to dial back that extreme brittleness and trade a little bit of that hardness for a whole lot of toughness. This crucial balancing act is called tempering. Section 3. The tempering touch. Our freshly quenched cleaver is now as hard as a file, but it's also as brittle as a potato chip. It's an unusable state, a blade that would fail the moment it was put to work. To fix this, we introduce the final and most nuanced stage of heat treatment: tempering. The goal of tempering is to relieve the internal stresses from the violent quench, and to convert some of that brittle martensite into a tougher form. It's carefully controlled reheating, much lower than the hardening heat. The blades, now cool and dark, are cleaned of quenching oil. Then they're placed into special tempering ovens. This is where we fine-tune the steel's final properties. Inside the oven, blades are gently heated to roughly 350–500 degree rough. The exact temperature is one of the factory's most closely guarded secrets. A lower tempering temperature gives a harder blade that holds an edge longer, but it's slightly less tough. A higher temperature produces a tougher, more durable blade, more resistant to chipping, but it may need sharpening more often. For a heavy-duty cleaver, we favor toughness, sacrificing a bit of hardness for impact resistance. The blades sit in the oven for a set period, usually a few hours, allowing trapped carbon atoms to precipitate out of the martensite. That transforms brittle, needle-like martensite into a refined, tougher structure. You can actually see the effect on the steel's surface. As it heats, it forms a thin oxide layer and changes color. Light straw yellow, darker bronze, purple, and finally blue. Those colors indicate temperature, and by extension, the steel's final properties. For a cleaver, we often aim for darker straw, or light bronze. When the tempering cycle is complete, blades are removed and air-cooled slowly. The process is now complete. The steel has been fundamentally and permanently altered. It is no longer soft, nor is it glass brittle. It now has the ideal properties for its job: hard enough to hold a sharp edge through heavy use, and tough enough to absorb repeated impacts without chipping or breaking. Hardening, quenching, tempering. This three-step dance is the true science behind a high-performance blade. Section 4. The rough grind. With the heat treatment complete, our cleaver blade now has its inner strength, but it still looks rough. The surface is covered in a dark layer of scale. It has no edge. A hard, tough, cleaver-shaped slab of steel. The next stop, the grinding department. Sparks will fly. We begin shaping the blade's final geometry, starting with the rough grind. Main goals: remove the scale, flatten the sides, and establish the primary bevel. The long taper from spine to edge. A skilled operator takes the blade to a large belt grinder. Wide belts, fast-moving belts, ceramic abrasive belt close-up. The operator holds the blade against the moving belt and removes material. Steady hand, good eye. Even pressure to create flat, uniform surfaces on both sides. Keep the blade cool, don't ruin the temper. Grinding creates friction and heat. Buckets of water cool the blade between passes. Edge geometry begins to form. The operator angles the blade to create the primary bevel. Cleavers need a thick, robust edge for chopping. The grind angle is more obtuse than a slicing knife. The grinder removes steel from both sides, forming a V-taper from the spine. This initial grind isn't sharp. It sets basic angles and removes bulk, dusty, noisy, physically demanding work. Operators wear respirators. Operators wear safety glasses. Operators wear thick gloves. By the end, the blade looks more like the finished product. Dark, rough scale gone. Satin gray finish from the belt. Basic shape refined. Primary bevel set. Ready for finer grinding, sharpening, and finishing. Our cleaver has come a long way. It has survived the fire of the forge, the shock of the quench, and the tempering heat. It's tough and hard. The rough grind has given it its basic shape, but it's still crude. The surface is coarse from the aggressive grinding belts. Now it's time for the finishing touches. We take the blade from a roughly shaped tool to a refined instrument. This next stage uses progressively finer abrasive belts. We are no longer removing large amounts of steel. We are smoothing the surface, erasing the deep scratches left by the rough grind, preparing the blade for its final finish. An operator takes the blade back to the grinders. The belts now have a much finer grit, requiring a steady hand and a keen eye to maintain flat planes and crisp lines. Each pass on a new belt removes the scratch pattern from the previous, coarser belt. This is a methodical process of refinement. Keep the blade moving constantly to avoid flat spots or uneven surfaces. Just like before, the blade is frequently dipped in water. Even with these finer belts, heat can build up quickly. We cannot risk overheating the steel and ruining the temper. As the blade moves through finer grits, its appearance changes dramatically. The dull satin gray starts to give way to a brighter, smoother surface. Depending on the desired final look, this can have many steps. For a standard satin finish, we might stop after a few finer belts. For a more polished finish, for a mirror finish, the blade would continue to even finer belts and then to buffing wheels, cloth wheels, felt wheels, wheels loaded with polishing compounds. This final buffing step doesn't remove any significant amount of steel. It smooths the surface on a microscopic level, creating a beautiful, reflective shine. This finishing process isn't just for looks. A beautiful finish is a sign of good craftsmanship. A smoother surface is more resistant to corrosion. Fewer microscopic grooves mean fewer places for moisture and food to hide, which helps prevent rust and makes the blade easier to clean. Every step in this factory has a practical purpose. After this stage, the blade is dimensionally complete with its final surface finish. It's smooth, clean, and ready for the most critical step of all, getting its sharp edge. Up to this point, our cleaver still has no real cutting edge. The primary bevel we ground earlier tapers down to a thick, safe line of steel. Now it's time to create the secondary bevel, the cutting edge itself. This is the part of the blade that does the actual work. The process requires immense precision. We're not just making it sharp, we are establishing a specific angle for balance between cutting and durability. A cleaver needs a tougher, more obtuse angle than a slicing knife. Getting that angle right is a job for a specialist. The sharpening process often begins on a slow-moving, water-cooled grinding wheel, or a specialized belt grinder with a very fine abrasive. An operator holds the blade at a precise angle against the moving abrasive. Maintaining that exact angle along the entire length, from the heel to the tip, is crucial. Jig's guides can be used, but the final touch often comes from hands-on experience. The water bath keeps the edge cool to prevent softening. After grinding, the edge is honed to refine it further. Honing is done on an even finer abrasive, like a ceramic rod or a leather strop with polishing compound. This removes the microscopic burr, a tiny ragged flap created during grinding. If the burr isn't removed, it folds or breaks off, leaving a dull edge. Stropping realigns and polishes the very finest point to a razor finish. The finished edge is tested by slicing paper and rope. The result is deceptively sharp. The apex is honed to a microscopic point. It's sharp enough to slice cleanly, yet strong enough for chopping bone. Two-stage geometry, long primary bevel, short secondary bevel, is the secret. The blade is now finished. It is hard, it is tough, it is smooth, it is sharp, but it still needs a handle. Section 3, the handle. Crafting the human connection. A cleaver blade without a handle is just a dangerous piece of metal. The handle is the interface between the tool and the user. It provides control, it provides comfort, it provides safety. Here in the factory, we make our handles, or scales, in a separate department. For a classic look, we use dense, durable hardwoods like rosewood. We also use paca wood, a wooden resin composite. For modern, high-use professional cleavers, we often use synthetic materials like G10, micarta. These materials are practically indestructible. They are waterproof. They offer a fantastic grip even when wet or oily. The raw material arrives, wood, composite, in large sheets or blocks. The first step is to cut the raw material into two symmetrical slabs. These are the scales that will sandwich the tang of the cleaver. This is done with precision saws to ensure a perfect fit. Next, holes are drilled through the scales. These holes must align perfectly with the holes already drilled in the steel tang of the blade. This alignment is critical for the final assembly. Once the holes are drilled, the scales are roughly shaped to their final ergonomic contour, using saws, sanders. At this stage, they are left slightly oversized. Final shaping and finishing happen after attachment to the blade. The tang of the cleaver blade is the foundation for the handle. As we've mentioned, we use a full tang construction for our cleavers. The steel of the tang has the same profile as the handle. It extends all the way to the back. This is the strongest possible construction. It creates a solid, unified tool from tip to tail. It provides excellent balance. It ensures the handle will never loosen or break away from the blade. Before assembly, the surface of the tang is often scuffed up or textured. This gives the epoxy a better surface to grip, creating an even stronger bond. With the scales cut and drilled and the tang prepped, we are now ready to bring these components together. The handle is more than just a grip. It's a crucial part of the tool's balance and feel. The weight of the handle material is carefully chosen to complement the weight of the blade, helping us achieve that perfect blade-forward balance we designed from the start. A well-crafted handle makes the tool safer and more comfortable to use. It completes the cleaver's transformation into a balanced, functional extension of the hand. The parts are all ready for the final marriage of steel and wood, or composite. Section 4. The final assembly, bringing it all together. This is the moment where all the separate pieces we've been working on finally become one. The final assembly is a careful, precise process that permanently joins the blade to its handle. First, the operator gathers the components. The finished blade, the two matched handle scales, the metal pins or rivets that will hold everything together. A thin, even layer of high-strength, waterproof epoxy is applied to the inside of each handle scale and to both sides of the steel tang. This epoxy serves two purposes. It creates a powerful, permanent bond and completely seals the gap between the steel and the handle material, preventing any moisture from getting inside. The two epoxy-coated scales are then carefully placed on either side of the tang, sandwiching the steel. The operator makes sure the pre-drilled holes in the scales line up perfectly with the holes in the tang. The metal pins, which are often made of brass, stainless steel, or nickel-silver, are coated with a bit of epoxy and then inserted through the holes. These pins pass through the first scale, through the steel tang, and out through the second scale. They are the primary mechanical fasteners holding the handle together. Once the pins are in place, the entire assembly is clamped tightly in a press or vise. The clamps apply even pressure across the handle, squeezing out any excess epoxy and ensuring a tight, seamless fit with no gaps. The cleaver will then sit in this clamp for several hours, or even overnight, to allow the epoxy to fully cure and reach its maximum strength. This curing process creates a bond that is so strong, the handle material would likely break before the epoxy ever gives way. Once cured, the cleaver is a single, solid unit. The blade and handle are now permanently joined, but the handle is still blocky and oversized, with the ends of the pins protruding from the sides. The final step is to shape and finish the handle. The cleaver is taken back to the belt grinders one last time. The operator carefully grinds down the oversized handle material and the protruding pins until they are perfectly flush with the steel tang. The handle is then contoured and smoothed into its final ergonomic shape, creating a comfortable and secure grip. Finer grip belts and hand sanding are used to make the handle silky smooth. Finally, if it's a wood handle, it's treated with oil or a sealant to protect it and bring out the natural beauty of the grain. The cleaver is now whole, a complete tool ready for its final inspection. Section 1. The seal of approval, quality, safety, and the final test. Before any cleaver leaves, it must pass one final stage: quality control. This isn't a quick glance. It's a rigorous inspection to meet our high standards. An inspector picks up the finished cleaver, fire, force, precision. They check it from top to bottom. Examine the blade for cosmetic flaws. Ensure the finish is perfect and lines are crisp. Run fingers along the handle, checking for gaps between scales and tang. Check for any rough spots. The fit and finish must be flawless. Next, physical tests. Check straightness. Make sure there was no warping. Test sharpness right out of the box by slicing rope or by slicing thick cardstock. The cut must be clean and effortless. They also perform a durability test, striking the edge, often against a hard nylon rod to ensure the edge doesn't chip or roll. This verifies the heat treatment, creating a blade that's both hard and tough. Only cleavers that pass all these tests get the final seal of approval. This dedication to quality is mirrored by our commitment to safety. You've seen the sparks, the heat, and the powerful machinery. This is a dangerous environment. Protecting our workers is our top priority. Everyone on the factory floor wears personal protective equipment: safety glasses, face shields, heavy-duty gloves, steel-toed boots. The air is filtered to remove metal dust, and every machine has guards and emergency stop features. We have strict protocols for handling hot steel and for operating the presses and grinders. A safe factory is an efficient factory. This final inspection is the promise we make to our customers. It guarantees a tool made with precision, strength, and safety above all else. Right materials were chosen. Forging was precise. Heat treatment was perfect. Final assembly was seamless. When a cleaver passes this final test, it's not just a product anymore. It's a testament to the skill of the workers and the integrity of the entire manufacturing process. It's ready for a lifetime of work in a busy kitchen. Section 2. From our factory to your kitchen. A tool for generations. So we've followed the journey from a simple bar of steel to a finished, sharp, and balanced cleaver. Now, how do you take care of this tool to make sure it lasts? It's simpler than you think. First, always hand wash your cleaver. The high heat and harsh detergents in a dishwasher can damage the handle. Dishwashers can also cause the blade to corrode. They can make the blade knock against other items, dulling the edge. Wash with soap and water. And most importantly, dry it immediately and thoroughly. High-carbon steel, even with chromium, can rust if left wet. Proper cleaning is the single best thing you can do for your cleaver. Don't toss it in a drawer with other utensils. All that clattering will dull the edge. A magnetic knife strip on the wall is a great option. A wooden knife block with a slot large enough for the cleaver also works well. A high-quality cleaver won't need sharpening often. When it does, use a whetstone or use a guided sharpening system. Remember the angle. A cleaver has a wider, more robust edge than a chef's knife. Maintaining that tougher angle prevents chipping during heavy use. A little care goes a long way. When buying a cleaver, know what to look for. Check for a full tang. See if the steel runs all the way through the handle profile. Feel the balance. It should be a bit blade heavy. Look at the finish. A seamless transition between handle scales and tang is a mark of quality. These details show the care in manufacturing. You now understand why a forged blade might cost more, and why heat treatment is critical. The journey from steel to cleaver is a story of transformation, taking raw material and, through immense force, turning it into a tool. Through precise science, through human skill, a high-performance tool built to last generations. Every step, from choosing the right alloy to the final polish on the handle, matters. It's a testament to modern manufacturing and craftsmanship. This is a tool with a soul, forged in fire and ready for your kitchen.